of opening the stage today, about my project, about my Android app, how it learns to talk to plants. So, a quick briefer about myself. I am James Gutt. I'm third-time speaker at droidcon Berlin. Some of you know me as an Agent Gutt. I went on many adventures with AOSP, because that is most of my background. Today, we're going a bit in the Android app territory. This project found itself into action at university. This is my IoT-enabled greenhouse project. It's a form of dissertation, final year project kind of idea, and it integrates an Android app, so I said, why not just submit this to droidcon, and here I am. So, today no agents, no secret stuff, we're just going to go straight to the motivation. So, why are we doing this? What's the motivation behind this project? We're going to have a system overview, which consists of hardware components, network configuration, software components, API and website infrastructure, and also finally the Android app architecture with some future works for future works. So, the motivation. There is a lot of people on this planet. We need a lot of food, hygienic food. So what's the solution to most of that? Greenhouses. They provide a way for us to grow crops of season, keep food going throughout the year, and scale farming to a big degree. So in this case, it's more work because you have a controlled environment. You want to keep these parameters as much as possible optimized for your crops. Which may vary. This may depend on temperature, carbon dioxide, light, soil conditions, etc. So, bit by bit, we need to find a way to control these parameters in a smart system which can give us a nice user interface for farmers to produce better crops. So, with hardware components, we have three major environmental sensors. The SED41 sensor gives us good readings and accurate results for temperature, relative humidity, and carbon dioxide. This has been tested and it works via an I2C protocol, which works with microcontrollers. The BH1750 sensor gives us an accurate reading for ambient light, which is important for photosynthesis. Some crops depend on more light or less light, so this will be useful for us to see how much lumens there is in the greenhouse. And outside the greenhouse, there is an anemometer, which will give us an ADC voltage reading between 0.4 volts, which we map to 0 meters per second, and also 2.0 volts, which is the maximum, which tells us the max speed, which is 32.4 meters per second for outdoor winds. I will explain why we are calculating the outdoor weather in a second. For soil sensors, we have a capacitive moisture sensor, which will tell us how wet the soil is, how much water there is in a certain zone. This is important, obviously, even in a household where me and many others may neglect some plants and kill them. So this is important for us to keep track of how much water there is for our plants. The SCN0603 sensor gives us a pH and an electrical conductivity measurement in microsiemens per centimeter. However, when I tested the sensor, the electrical conductivity was not so accurate, so in academic prospect and also in just truthful data, I neglected this data, but the pH value was quite accurate to a very close degree, so we kept that sensor in the mix. Finally, we have the SCN0605 sensor, which is measuring nitrogen, phosphorus, and potassium contents in soil. If we're using fertilizers and also some other chemicals, this is important for us to track contents in ratios. So in this case, it promised micrograms per kilogram, the sensor, but unfortunately, I had to map it with different chemical soil samples so that it is more accurate in terms of ratios to 10. With these hardware sensors, we also have a system which consists of actuators. So in this case, for prototyping reasons, I'm using DC components, so direct current components. We have a PWM control fan, so this gives us variable speed. As mentioned before, we are tracking temperature, and with the fan, we can also exhaust the heat out of the greenhouse, so if it is too hot or if there is even smoke, we can detect that with carbon dioxide and blow the bad smoke out and also cool the temperature down. With water, a pump is important, so if we have a threshold of 20% of moisture. We just trigger this pump and it will automatically water our crops accordingly. Linear actuator is going to simulate a window. So when I mentioned that we have an anemometer to detect wind speed, this will also help with the linear actuator. So in this case, if we have enough wind outside, we just open the window instead of ramping the fans to full. So we also do our part to save power on battery. And this is obviously towards a greener environment, a safer world for us. And yeah, if it's on batteries and solar panels, super useful. Finally, we have a variable angle servo motor. You can buy these off the shelf. Obviously, this will scale for a greenhouse system, but this will give us a flap for more light to enter the greenhouse and also more airflow. For the microcontrollers, the brains of the system, which consume up to 4 watts when fully triggered with the actuators, we have an ESP32S3. I'm sure some of you might have heard about this. It's an embedded board. It has a lot of pins, a lot of interfaces for our sensors and actuators, and also has 32 megabytes of PS RAM. So yes, we might say 32 megabytes is fairly little, but we will make use of that, that storage momentarily when I explain the further features. It has Wi-Fi and Bluetooth Low Energy, so in this case we will be making API requests to a server, which I will explain later. But thanks to that, we will have the necessary pins and interfaces to make the system work. Additionally, later on, when we have 2 systems with the actuators and sensing, I used a LoRa-enabled ESP32, which is long-range wireless protocol, and this will make the ESP32s talk to each other seamlessly so that they can transmit data and the other one can react upon the data that is received. Okay, enough hardware, let's go about the network configuration. So these systems will be set up in node-to-node communication. What we have is one sensing unit, one actuator unit. Using LoRa, they speak to each other, they connect, the sensing unit connects to Wi-Fi, and then that Wi-Fi interface will be our gateway to an API request to our web server. Once we get connection to the internet, the server on my end, so this is my room, will download that API, so download the data, store it on a local MySQL database, and then push it on a GitHub repository because it's a free platform for everyone to observe data, and it is indexed in .json files so that it is easy for us to turn into graphs and yeah, make easy readings possible. When we have sensing, we also have flowcharts, so there's a sequence to this. We have a setup which interfaces all the sensors, times all the different readings. So in this case, we have ADC comes after UART sensors and I2C comes before everything, so the time is important here. After those are initialized, we have a loop which repeats every 30 seconds, and every 10 minutes it will upload it to the API server, which will download the data on the server. For actuator, we establish a LoRa communication, we establish the linear actuators, the fans, etc. And according to thresholds, so in this case temperature, humidity, carbon dioxide, light, and moisture thresholds, it will start behaving automatically. So if a farmer is away from his greenhouse, it will automatically take over and make sure that everything is in optimized conditions. Obviously, these may vary according to what crop you have, but in this case, it's adjustable for different reasons. Okay, we have an image processing aspect. This is obviously very fundamental and basic in the sense. I made another website which anyone can upload their pictures to. So I take a picture of a leaf. This will be sent to a queue, and then the ESP32 will keep checking for this queue and download the image to the PSRAM in 480p. Once that is done, it will get this algorithm, put a bounding box ratio after the text that there is a leaf in the image, and then start passing some tests, so green pixels to yellow pixels, the edge detection to see if it's crumbling, the edge density, shape metrics, aspect ratio to determine whether the leaf is healthy or unhealthy. Obviously using an LLM model, and even MobileNet v2, which can be sizable on a phone, would be more accurate, but in this case this is a broader range of plants which are mostly green. So when you're doing LLM, you have to specify what crop you're looking after because they will vary on the characteristics of decay. So that's important. Now getting to the interface and the applications, there's a QR code here which will take you to my website, which is self-hosted. It is IoTgreenhouse.info. And if you have an Android phone, you can also go on the Google Play Store and look up IoT Greenhouse, and you will have the leftmost interface of the application. So let's start discussing how we did this infrastructure. And the backend, so on the server side, not on the greenhouse side, we have an API server running with Flask, which is a Python program. I am using Docker Compose to get everything together, obviously, as you can see on the screenshot over here, where we define our API server, my SQL database, which is a local database. But essentially, we just have a simple REST API endpoint, which we will call, request, with an authenticated manner. Obviously, we don't want anyone pushing false data or sabotaging our system. So there's a password, and even in future terms, when I want to work on this in a more larger scale, I will add more security endpoints to the whole transmission of our data. The API and the REST endpoint will be used for both the website, for the live dashboard, which will give us the most recent data, and the Android application. So we are using that for both of the applications. For the front end, so the website part, I use Astro, which is a JavaScript framework. It is very simple to get to make nice interfaces. For this tile setup, this was most convenient, and I also had the liberty of having more complicated situations like uploading images, downscaling them, and then pushing them onto a results on the queue page, so that was very good. As I said, this is self-hosted. I personally am not a fan of port forwarding from my PC, so in this case I use Cloudflare Tunnel, which is a free way to get your domain and your server connected, in this case. So in the Cloudflare and the Docker Compose, I specify a Cloudflare container, and from there I have greenhouse.pixelboot.dev so that it transmits the Astro framework and the ports as accordingly. Okay. For the Android app architecture, something more interesting in line with droidcon. I am using an MVVM, a model view model architecture. So in this case, we have a screen, which is either a dashboard, a history page, or a weather page, which is a screen. The view model is it is distributing the workload, the coroutines we have also working in the background, and the model is associated with the data we are receiving. So in this case, the APIs, the databases, the indexing of JSON files accordingly. I'm using Jet.compose. Before I used XML views, it was a bit uglier, and even when scaling with fonts, it wasn't as convenient, and most people now use Jet.compose. So I followed the trend. And we have state management, so in this case we define explicit states and transitions so we don't make extra refreshes in our app to save battery life and CPU resources, obviously to make it also just more optimized. I use Moshi with reflection, which is a library, so that in this case I parse the different files, they are all stored on the app, and on runtime everything is running well. It's not breaking and falling apart. Coroutines, so that we can offload tasks whenever there needs to be a suspend, an active task, and we don't obviously disturb the main thread, so the UI remains as optimized as possible. Image loading we use Coil, so Coil gives us those weather icons in the weather component, which we will discuss later. And retrofit and OKHTTP to make these API requests and calls for our application. So the first screen we have is a home screen. The goal of the home screen is to give you an easy user interface which you can scroll through. So you have climate conditions on the top part and soil conditions at the bottom. The most challenging parts of this is to define what variables we have, what layout and template we have for each different parameter. And we also need to handle null values. So in this case, we can have a zero because there can not be wind, for example. As you can see up there, it's 0 meters per second. And also, if something goes wrong, the application doesn't hide elements and crash accordingly. So each data model will be resilient to nullable variables and values. On the other end, for front end, we have an adaptive grid UI. So I used lazy vertical grid. So in this case, it will move about according to what screen you have, either a tablet screen, a large foldable, or also a normal handheld, a phone. And it also adapts to font changes. So if we have a big font and it uses 2 lines instead of 1, I symmetrically put every tile to 2 so it doesn't look like it's going all over the place. Stateful UI is important because if we don't have the data, if we are offline, we need to show the user that there is no internet connection and that he needs to connect to the internet. So making explicit states for each different process, making calls, etc., and also showing the user what's going on happens over here. So again, not too many things going on, very simple, I'm sure everyone can follow. Moving on to the history screen. This is where I had a bit of trouble, especially when moving to Kotlin and Jetpack Compose. I didn't manage to integrate native graphs yet, and also the nature of the JSON files is very sporadic. So the greenhouse may be offline from 8 p.m. to 8 a.m. So hence we have gaps in the x-axis time variable. So in this case, I said, let's play it safe. There's a time constraint as well. I'm just going to make a web view container, which will show me the website from IoT-greenhouse.info to show me the graphs on JavaScript built high charts. So in this case, I just made a feature-rich embedded web view, which will give us scales for day, week, month, and year, and also show Kia, which is when I went on site in an actual greenhouse. That one has the most data. If you currently see no data, that's because the system has been offline for a couple of months because I was submitting my proposal and it was used in expose and all sorts of events. So in this case, the show key will give you good data. There's a JavaScript injection code. So in this case, I will tell the Android application, hey, hide the navbar and the footer so that it doesn't look like a website and it looks more integrated in the website, the application itself. So that's the second thing I did, and the last thing I did was also follow along the native error UI to tell the user, hey, you don't have internet, at the same time don't show that Android error message in the top left when you have a web view without internet or an unreachable site. It will just show you a native Compose UI, so it is more integrated with the application. Finally, shout out to Shoki and Gozo. We are showing whether for the next 5 days, this is useful for farmers to predict how the ambiental parameters will change. If rain is coming along, if there's going to be a thunderstorm, less light for solar panels, so this is quite an important interface. In this case, I have grids of each day, so in this case, the next 5 days, starting from top left to bottom right. And I also have a small scrolling method that I used. It's a ticker, and it will show you each hour how the temperature will change. This is more important if there's going to be a abrupt change, so you have days and also hourly forecast. In this case, I'm using Open Weather API, which does give you limited tokens. So in this case, on the back end, I cached every 3 hours, so that we don't run out of tokens, and if somebody keeps refreshing their weather page, they don't get kicked out of the service. I'm using a repository pattern, obviously. It collects the 2 different aspects of this. So in this case, you have the raw API call with the hourly weather, and then you also have a more structured categorization for each day. So handling both different API layouts is kind of important here, and that's what the app is doing. At the same time, we are using a composable UI again, so that everything looks good on different screens. And yeah, it's basically the 3 screens. So let's talk about the last part of this talk is going to be discussing about future work. There is a big demand for notification support. When I spoke to farmers in Shokia and also places around Malta, it is useful not to optimize and completely go remoteless without any farmers. It's more important to advise of the changes, so having alert and notification support can help us alert farmers of, hey, you need to plant this crop, this zone is going out of moisture, and it will just be a utility more than a replacement of a system. As well, NDVI leaf health analysis. It is important to keep track of how your leaves are doing. In this case, using my image processing algorithm, it's not the best. So when you normalize the difference vegetation index, which also has a sensor with it, you can put a leaf over a white surface, and this sensor will tell you how much chlorophyll you have, more details about how the plant is decaying and what nutrients it might need. So this would be more useful for if you have a larger fertilization needs, specific crops for different times. So this is a more advanced and future-proof system. At the same time, I didn't have a LoRaWAN gateway in my network setup. This is useful if the internet connection in the greenhouse abruptly cuts out. In this case, the LoRaWAN gateway will be the interface between the sensing node and the internet. So in case there's no internet, it will start caching, storing it in a database. Once the internet comes back alive, it will also publish that on the web. At the same time, the LoRaWAN gateway will give us a way to scale larger systems. So in this case, all the ESP32s will connect to one point, and then at one point, we'll make a push to the API server and then on the website infrastructure. Actuator control, so far it's fully autonomous, but at the same time, if something goes wrong, if the farmer needs to take control, it's a good idea to have a web and app interface so that you can stop the actuators from automatically moving forward, and also like override to different conditions accordingly. Essentially, that is all about it, and I am happy to hear your questions from the two microphones. Thank you. Also feel free to come talk to me afterwards. So if you don't feel like, if you stage fright, I'm always here to take your comments, your questions, and maybe even some improvements. Thank you very much.